Hello. So, I had originally planned on doing a video on the neutron current and going over that quite completely. However, I found that in my attempt to purvey the subject, that it couldn't quite be understood. I couldn't quite get across the meaning that I wanted to. So I think before I can begin a discussion of neutron current, I really need to discuss a bit more about angular flux, the angular flux phi of r, e, and omega. What is this really, the definition of it rather than the interpretation of it? So, I'm using steady state. However, you could also use a non-steady state formulation of it. So, the definition of the angular flux here, according to not no Carl Ott, is that the angular flux, if I were to draw a position vector from some sort of origin to a position r, and then at r I were to draw a unit plane or surface area element with a normal direction omega, then what your angular flux measures here is the net number of neutrons with energy E passing through the surface. Okay? That's the angular flux. And as you recall before, we also said the angular flux was defined to be this, or interpreted to be the path length generated by neutrons traveling in this unit volume per second in that energy range at that solid angle. So if we were to pull the neutrons traveling at a solid angle omega at energy E at position R, and we were to populate the space with that, then that would give us the path length traced out in 1 second by those neutrons. So the question then becomes is how do we get this interpretation from this definition? And the answer to this, I think the book by Zifwell, and I might be mispronouncing his name or butchering it. Maybe there's an I in there. Sorry, I didn't do my research too well. It's a thin book, and it likes to make use of the notion of Green's functions quite a bit. It has a very good interpretation of this, but basic idea is if you were to take, Zifwell uses a cylinder, but I'm using a plane because I find planes a bit easier to draw. If you were to take your unit plane through which your neutrons are passing through, and it has some sort of unit normal vector omega. The idea is that if you were to start your stopwatch at t equals 0 and were to count out were to start measuring all the neutrons that were passing through that plane. In fact, let me take a side view of it. This is side. This is some sort of projection view. You're going to have a neutron, say, starting here at t equals 0, here, so on and so forth. And then in 1 second's time, they're going to trace out these paths. And as you can see, we can sort of extend this plane by a distance v related by E equals 1/2 mv squared. sorry, that's just v, not v dot, times 1 second. So if they're going at 2,200 meters a second times 1 second, so that's the distance is 2,200 meters. So that's the neutron velocity times 1 second. So that gives us a distance that this is sort of extended out to. So you can see here that if we were to sort of interpret this as the volume extended by the plane in 1 second's time, by the neutrons that start here and end up here at some time later. This will give us the path length traced out. And excuse sort of the hand wavy explanation of that. But basically what I want to get across is that when I think about the interpretation of angular flux, what I'm thinking about is a path length traced out in 1 second in that 1 cubic centimeter volume. Whereas when I'm thinking about the definition, this is the definition, this is the interpretation. When I'm thinking about the definition, on the other hand, I'm thinking more along the lines of this sort of idea here, where we have our unit surface area rather than volume. And this is the net number of neutrons. And where this becomes particularly important is in the idea of the neutron current. So if I were to have here's a side view, or I can do a projection view actually, of my unit plane, and I have a beam of neutrons here, I1, and a beam of neutrons going the other way, I2. The net number of neutrons passing through this, if the magnitude of the first beam equals the magnitude of the second beam, then the net angular flux passing through here is just going to be equal to 0. Okay. Now let's introduce a. Sorry. Excuse my wording. The net angular flux is going to be twice the intensity of either beam 1 or beam 2, because what the angular flux measures is the net number of neutrons passing through this plane. Okay. This is distinct from another concept we refer to as the neutron current, and it's a vector quantity. We call this the neutron current. Okay. And the neutron current is interpreted as the net number of neutrons passing through the plane. So the flux here, phi, this is, and you know, I don't like the language I'm using here. I can call this the total, but you know, what's the distinction between total and net? Maybe I can call this the net leakage of neutrons, whereas this is the net number. And let me just try and explain this, and maybe it'll make some more sense. If I were to have this unit plane again, and I were to have my beam 1, and my other beam here, and they're of equal magnitude, then J equals 0. Okay? But if this is I1 and plus 1 more neutron per centimeter squared second, then this is just going to be one traveling in that direction. So it's the net number of neutrons. Maybe I can just read out the definition. Yeah, the fact that J describes the net motion of neutrons is what the wording that the ought uses. So I guess what I want to get across is that the angular flux here, every neutron that passes through this plane here tallies it up by 1. On the other hand, the current here, if we have a neutron going this way and then another neutron going the opposite direction, then that's just 0. If we have 2 neutrons going this way and 1 neutron going that way, then that's just 1 going that way. So that's the sort of introduction to the distinction between angular flux and current, and next video I'll get into a bit more of a formalism about it. Thank you and have a nice day.